This video introduces multi-protocol label switching, or MPLS. We will cover the drawbacks of traditional IP forwarding, basic MPLS concepts, its architecture, and how it compares to IP over ATM. We will also discuss traffic engineering with MPLS, labels, label switch routers, and its advantages and disadvantages. Traditional IP routing, as the first defined protocol for global internetworking, has several disadvantages. It is connectionless and lacks quality of service, or QoS. Routing protocols distribute Layer 3 information, and lookups must be performed at every hop. Further disadvantages of IP routing include a large IP header, at least 20 bytes, and routing occurring in the network layer, which is slower than switching. It is usually designed to find the shortest path, not taking additional metrics into account. Asynchronous transfer mode, or ATM, is a connection-oriented technology that supports QoS. It allows fast packet switching with fixed-length cells and integrates different traffic types like voice, data, and video. However, ATM also has disadvantages. The disadvantages of ATM include its complexity, high expense, and limited widespread adoption. MPLS was introduced in the late 1990s to accelerate network traffic. It replaced the slower, software-based IP routing table lookups with faster, label-based switching. MPLS is a new forwarding mechanism where packets are forwarded based on labels. These labels usually correspond to IP destination networks, similar to traditional IP forwarding. They can also represent other parameters like QoS or source address. MPLS was designed to support forwarding from multiple protocols. MPLS conceptually combines the forwarding algorithm used in ATM with IP, creating a hybrid approach between IP's packet forwarding and ATM's circuit switching. Multi-protocol label switching is positioned between Layer 2 and Layer 3 of the networking model, often referred to as Layer 2.5. MPLS characteristics include mechanisms for managing various traffic flow granularities. It is independent of LAYER2 and Layer 3 protocols, mapping IP addresses to fixed-length labels. It interfaces with existing routing protocols and supports ATM, frame relay, and Ethernet. The MPLS architecture consists of two major components. The control plane exchanges Layer 3 routing information and labels. The data plane is responsible for forwarding packets based on those labels. The control plane uses complex mechanisms to exchange routing information, utilizing protocols like OSPF, EIGRP, ISIS, and BGP. Label exchange is managed by protocols like TDP, LDP, BGP, and RSVP. The data plane, conversely, operates with a simple forwarding engine. MPLS technology is designed to be used regardless of the underlying Layer 1 media and Layer 2 protocol. It inserts a 32-bit label field between the Layer 2 and Layer 3 headers. The 32-bit MPLS label field contains four components: a 20-bit label, a 3-bit experimental field, a 1-bit bottom-of-stack indicator, and an 8-bit time-to-live, or TTL field. This diagram illustrates the structure of the 32-bit MPLS label field and its components. This image shows the generic label format, positioned between the link layer header and the Layer 3 header, along with the detailed structure of the 32-bit label. Usually, only one label is assigned to a packet. However, scenarios like MPLS VPNs require more than one label. For VPNs, the top label points to the egress router, and the second label identifies the specific VPN. MPLS traffic engineering, or TE, uses two or more labels. The top label indicates the endpoint of the traffic engineering tunnel, and the second label points to the destination. Combining MPLS VPNs with MPLS TE can result in 3 or more labels. This graphic illustrates the process of label distribution, where a packet undergoes a routing lookup and label assignment before being forwarded with the MPLS label inserted between Layer 2 and Layer 3. The IETF defined the Label Distribution Protocol, or LDP, for explicit signaling and management of labels. Extensions to LDP have been defined to support explicit routing based on quality of service requirements. A label switching router, or LSR, is a high-speed router in the core of an MPLS network. Its primary function is to forward labeled packets through label swapping. An edge label switching router, or Edge LSR, also known as a label edge router, or LER, labels incoming IP packets to forward them into the MPLS domain. It also removes labels to forward IP packets out of the MPLS domain. This slide visually represents the LSR and Edge LSR components within the network. This diagram illustrates the positions of the label edge routers and label switching routers within a network architecture. All LSRs perform three key functions: exchanging routing information, exchanging labels, and forwarding packets. The first two belong to the control plane, and the last is part of the data plane. This slide further illustrates the architecture of label switch routers. This slide further illustrates the architecture of edge label switching routers. In MPLS terminology, a label is an identifier indicating the path a packet should traverse. It is carried with the packet, and the receiving router examines it to determine the next hop. Once a packet is labeled, its journey through the backbone is based on label switching, speeding up routing decisions at each intermediate router. Label creation involves assigning a unique 20-bit label to every entry in the routing table. Swap is the action of replacing an incoming label with a new outgoing label, forwarding the packet along the new path. Push is when a new label is added to the top of the packet, encapsulating the original IP packet in an MPLS layer. POP is the removal of a label from a packet. If the last label is popped, the packet leaves the MPLS tunnel. The LER, or Label Edge Router, operates at the network's edge and performs push and pop functions, acting as the interface between the access and MPLS networks. An LSR, or Label Switching Router, is a high-speed core router that performs swapping and establishes the label switch path, or LSP. Ingress routers perform the first push function, and egress routers perform the pop function. These are both LERs. Label switched paths, or LSPs, are established before data transmission begins. An LSP is a representation of a forward equivalence class, or FEC. A forward equivalence class, or FEC, represents a group of packets sharing the same transport requirements. A packet is assigned to an FEC only once when it enters the network. MPLS offers two options for LSP setup: hop-by-hop routing, where each LSR independently selects the next hop, and explicit routing, where the ingress LSR specifies the entire path. LSPs are unidirectional, meaning return traffic requires a separate LSP. The Label Distribution Protocol, or LDP, is an application layer protocol for distributing label binding information to LSRs. It maps FECs to labels, thereby creating LSPs. LDP sessions are established between LDP peers, sometimes employing OSPF or BGP. LDP uses four types of messages: discovery messages, session messages, advertisement messages for label mappings, and notification messages for advisory and error information. Traffic engineering in MPLS is inherently supported using explicitly routed paths. LSPs can be created independently based on user-defined policies. RSVPTE and CRLDP are two approaches for providing dynamic traffic engineering and QoS. RSVPTE allows for requesting bandwidth and traffic conditions along a defined path. Its drawbacks include requiring regular refreshes and scalability challenges. CRLDP considers parameters such as link characteristics, hop count, and QoS. This allows for selecting a longer, less loaded path over the shortest, most congested one. However, it adds complexity to routing calculations. For a data packet to traverse an MPLS domain, several steps must occur, including label creation and distribution, table creation at each router, and label switched path creation. This is followed by label insertion, table lookup, and finally, packet forwarding. This slide is a continuation of the previous one and pertains to MPLS operation. MPLS offers several advantages, including faster packet forwarding, support for quality of service and class of service, network scalability, and robust traffic engineering. It also integrates IP and ATM and builds interoperable networks. The disadvantages of MPLS include adding an additional layer, which can be costly. Routers must understand MPLS, and deployment can be slow with low flexibility. Thank you for watching this video on MPLS.